Hello friends, welcome back to another engineering science recap video. My name is Jason. I am in my third year of engineering science, specializing in biomedical systems engineering. Today is September 9th, 2022, the start of a new school term. And today I will be talking about the course PHY294, Quantum and Thermal Physics. This is actually the last video I'm recording for um, the year 2 winter courses. After this, I will be doing my third year fall term, and then after I finish those classes, I'll be making videos again for those classes in particular. But after this video, uh, I will be gone for a couple of months. But yeah, let's just get right to it. So PHY294 is a second year winter course in the Engsci curriculum at U of T. When I took this course, the course and practical coordinator was Dr. Ruxandra Serbanescu, and the lecturers were Professor R.J. Dwayne Miller and Professor C. Barth Netterfield. So this course is split into two halves. Obviously, we have quantum physics and we have thermal physics. So for the first half, we got obviously our quantum mechanics review. We spoke about the hydrogen atom and its solutions, the Pauli exclusion principle, Hund's rule, periodic trends, the Zeeman effect and the anomalous Zeeman effect, the Lewis octet rule, molecular orbitals, electronegativity, hybridization, hydrogen bonding, and spectroscopy. So it's not really a traditional quantum physics course, but we cover more of the chemistry side of things. So more like quantum chemistry, and a lot of it was review from sort of grade 12, if you went to high school in Ontario. And then for the second half of the course, we get more into uh, thermal physics, aka like statistical mechanics. So we start off by talking about the ideal gas law, then we get into the equipartition theorem, macrostates and microstates, Einstein solids, large number approximations, ideal gas multiplicity, what temperature is, thermodynamic identity, Boltzmann factors, Maxwell speed distributions, free energy, Gibbs factors, bosons and fermions, and then at the end of the course we get into a little bit about blackbody radiation and Debye theory. So today I'll be going over an interesting question from term test 1, which was from the quantum half of this course. It was administered on February 17th, 2022, and the topics it covered included the variational method, which is a way of looking at the electron energies around in a certain atom, in a multi-electron atom. Then we look at effective nuclear charge, binding energy, and electron correlation energy. So there's a lot of context for this question, so let's just get right to it. First of all, we're given an introduction to the variational theorem. So the variational theorem is important in providing reasonable approximations to the operating physics in multi-electron atoms, as I mentioned earlier. The exact solution is always lower in energy than any approximate solution, so that's important to keep in mind. A particular trial function for helium using hydrogen 1s wave functions can be written as psi of R1, R2 is equal to psi sub 1s of R1 times psi 1s R2, and this is equal to e to the minus z times R1 plus R2. So using the nuclear charge z as a variational variable, so we could replace z in the exponent with alpha instead, which is just an arbitrary parameter, we can find the lowest energy and effective nuclear charge, assuming 1s electron distributions. Using the above trial function with the Schrödinger equation to calculate the energy E, after a bit of math, one arrives at the relation for energy for the helium atom in terms of the variation variable as the following. E of alpha is equal to alpha squared minus 27 over 8 alpha. So this whole derivation is done for us. We don't have to worry about it too much. It's just given in the context of the question. Note that this expression is in atomic units or Hartrees to keep things simple. one Hartree is equal to 27.211 electron volts, or twice the Rydberg energy, which is basically the energy of an electron in the lowest energy state in a hydrogen atom. Alright, so part A. Using the above expression for E of alpha, what is the effective nuclear charge, Z effective, also known as alpha, felt by the electrons in this approximation? And we're told that in order to find this value, we need to find the minimum energy with respect to the variational variable alpha, and offer an explanation why Z is greater than 1, i.e. that each electron does not screen its full complement of a proton charge in the nucleus. Part B, with your estimated Z effective, or alpha value giving the lowest energy, calculate the energy of the helium atom within this approximation. You need to convert Hartrees to electron volts. We would like Part C, we would like to compare this approximation using the variational method to the exact energy. Since this problem cannot be solved exactly, we need to experimentally measure it. The first ionization energy, if we were to shoot a photon at the helium atom to ionize it, is found to be 24.6 electron volts. With this information, what is the exact energy of the helium atom? Hint, you need to calculate the second ionization energy from helium 1 plus to helium 2 plus. And finally, part D, the error in this simple calculation is quite small, 2 to 3%. Please describe physically what the difference in the approximate energy and exact solution is due to. The interesting point is that this energy is comparable to chemical bonds, and it is for this reason accurate calculations with higher levels of approximation are used in quantum calculations of atomic/molecular properties. Alright, so let's do part A first. What is the effective nuclear charge? So we're given this equation using the variational variable alpha for the total energy of the helium atom. And again, what we want to do is we want to find alpha such that the energy is minimized. So what we can take the derivative of energy with respect to alpha. We do that, we get an expression 2 alpha minus 27 over 8. If we set this to 0 to find the local minimum, notice how the parabola opens upwards so that there should be exactly one local minimum, and that would be at the vertex of the parabola, and we'll find that this minimum value is equal, or the minimum energy is achieved when alpha is equal to 27 over 16. And recall that our Z effective is simply alpha sub min, which is where the energy is minimized. So Z effective is 27 over 16, which is 1.6875. Notice that this value is greater than 1, but less than 2. This is very important this is because of the incomplete screening of the nucleus by each electron due to the spatial distribution of the electrons. So recall that helium has 2 protons and 2 electrons. And so if you were to consider one electron without considering the other, then we would likely say that the electron should experience an effective nuclear charge or it should experience a nuclear charge of 2, right? Because it's screening both protons in the nucleus. But when we have 2 electrons, there's incomplete screening of the nucleus because the electrons will essentially interfere with that screening. Their spatial distribution will depend on the other electron, and because of that, the Z effective will be lowered, and so it won't be 2, but also it will still remain greater than 1 because each electron will screen slightly more than just 1 proton. So using this calculation, we approximate it to be around 1.6875. So part B, now we want to find the approximate energy of the helium atom. Remember, we're given this equation for energy, and we already know the value of alpha that minimizes the energy, which is 27 over 16, and we know the conversion from Hartrees to electron volts. So we just plug in our value for alpha, which gives us the minimum energy, and the energy is approximately minus 2.85 Hartrees, and we would convert this into electron volts. It's negative 77.49 electron volts. So therefore, the approximate binding energy of the helium atom, the energy contained in the attraction between the protons and the electrons, is negative 77.49 electron volts. So part C. Now we want to calculate the exact energy, the exact binding energy of the helium atom. And we know that the exact energy is going to be the sum of the first and second ionization energies. We're given the first ionization energy in the question, negative 24.6 electron volts, and we want to find the second ionization energy. What we notice is that the second ionization energy occurs when we go from helium 1 plus to helium 2 plus. And what we should notice is that helium 1 plus is a hydrogen-like atom. So what we can do is we can use this formula, the energy of the valence electron is going to be equal to minus z squared over n squared of the Rydberg multiplied by the Rydberg energy, where the Rydberg energy is 13.6 electron volts. So because there's one electron in the helium 1 plus hydrogen-like atom, we'll use n equals 1 to represent the lowest energy state. This is also known as the intrinsic binding energy. And we use Z is equal to 2 because helium has 2 protons in its nucleus. So we can calculate the second ionization energy. It's just equal to minus 4 E sub r, which is negative 54.4 electron volts. So the exact binding energy of helium is equal to the sum of the two ionization energies. When we sum them together, we get negative 79 electron volts, which is very close to the approximation we just did in part B. So now we want to compare our approximation and the exact energy. So using the trial function in the variational method assumes the average static charge distribution that the two electrons experience. Now this is not exactly what happens in real life, because the electron-electron repulsion will actually correlate the motion of the two electrons, because they want to be as far away from each other as possible due to their like charges. And because their motion is correlated like this, there's energy associated with this repulsion, and it's called electron correlation energy. And this explains why there's a difference between our approximate value and the exact energy we observe. And if you'll recall, the approximation was slightly higher than the exact energy, and that's because that is simply a result of the variational theorem, which states that our approximation will always be slightly higher than the exact value. So that was a really interesting question. And before I end off this video, I'd like to make some quick acknowledgements. Thank you once again to the instructors and course coordinator, Dr. Serbanescu, Professor Miller, and Professor Netterfield. I also would like to thank my tutorial TA, Vincent McKay. And I'd like to acknowledge the individuals whom I took this Beamer template from. So thank you very much, and I'll see you in the next video. Take care.